Welcome back to this final video in our FP1 series of videos. This one's using mathematical induction again, but this time to prove statements involving matrices. And what we're looking at is matrices raised to a power being equal to another matrix which generally involves powers inside it. So it's just proving that two matrices are the same. Okay, so for example, something like this, 0, 2, and this being equal to that matrix. So it's about proof, okay, and it's the same for basic steps. The basis step, the assumption, the inductive, and then the conclusion. Okay, so let's get into the first example. So here we have our first example, prove by induction that for all positive integers n, this matrix equals this matrix. And this is a past paper question. So the first step is, like in a lot of this, we're going to look at n equals 1. Okay, so let's look at the left hand side first of all. And that is 1, 2, 0, 1 raised to the power 1. Which is 1, 2, 0, 1. Now let's look at the right hand side. And this is 1, 2 times 1, 0, 1, which is 1, 2, 0, 1. So the left hand side equals the right hand side when n equals 1. So that's my basis step done. Now my assumption step. So assume that the matrix equation is true for k, n equals k. And that would mean then that we have 1, 2, 0, 1 to the power k equaling 1, 2k. Sorry, I messed up a little bit there. Right, so that is our assumption step. Now we're getting on to the inductive step. So for this now we want n equals k plus 1. Okay, so the matrix equation becomes, now you don't have to put in all of these words, but I'm just doing it to help you out, to fill it out completely. So 1, 2, 0, 1 and k plus 1. So now we're only dealing with this left hand side. Okay, and what we want to do is get to the right hand side but with a k plus 1. So with this a power k plus 1, we can split this up into the power k multiplied by the power 1. Okay, Now this is coming from my assumption step. So this is going to equal 1, 2k, 0, 1, multiplied by 1, 2, 0, 1. Okay, so we've replaced this using this assumption here with this. So we get this times this here. Now I need to do matrix multiplication. So that means I'm going 1 times 1 and 2k times 0. And that's going to give me 1 there. Now for this step, 1 times 2 is 2. 2k times 1 is 2k. So 2 plus 2k. Now for this one, so 0 times 1, 1 times 0, that's 0. And then for this one, 0 times 2 and 1 times 1 is 1. So that's what we've got. Now this is 1. 2 outside gives me a k plus 1 inside, 0 and 1. And this now is the right hand side with k plus 1 replacing the n. What I would say with this, guys, is while I've multiplied here to jump down to this case, in some cases when you multiply, you'd effectively just get this, just get the final bit. In those cases, I would show more of my workings in the multiplication. Okay, just to guarantee your marks, because it is a proof. You need to make sure that you show that you know exactly what you're doing and you're not skipping steps. Okay, so therefore the matrix equation is true when n equals k plus 1. Now that's the induction step complete. All that's left now is for the conclusion. And there we have it. So if the matrix equation is true for n equals k, then it's been shown true for n equals k plus 1. As the matrix equation is true for n equals 1, it is also true for all positive integers of n by mathematical induction. Okay, so that's pretty much all there is to it. There are obviously different types of questions, but they're all pretty much the same. So I'm just going to stick with this one example. I will do a couple of questions. I'll pick out a couple of past paper questions here for you to have a go at. And yeah, anyway, if you are enjoying the video, well, that's a strong word, isn't it? But if you're finding the video useful so far, please hit that like button. If you're yet to subscribe, hit the subscribe button now. And if you are, feel like you're able to help me out a little bit financially, then hit that join button. Even if it's just for a month, every little helps, and it does massively help me make these videos, and also will aid me in making more in the future. Anyway, let's look at the questions. Okay, here they are. I'm just going to give you two questions. Like I said, they're quite straightforward. If you can do these two questions, then you can certainly do this proof by induction of matrices. Be aware though, in the exams, they're not always straightforward. They sometimes involve other things with matrices. They might involve other types of manipulation, like the part A might be a proof, but part B there might be something else with matrices. Okay, so take it as a pinch of salt that we're just looking at the proof part, but in the exam the question might not just involve a proof by induction. Okay, so pause the video now, have a go at these, and then we'll look at the answers. Okay, it's question 1, and it's the same start for all of these. N equals 1. So looking at the left hand side, this is 3 minus 4, 1 minus 1 to the power 1, which is 3 minus 4, 1 minus 1. I know that's kind of obvious, you know, this is this, but you do need to put it down because you are doing a proof after all. So this now, substitute the 1 in for n. So 2 times 1 is 2, plus 1 is 3. That's 1 minus 4, and minus 2 plus 1 is minus 1. So there we have it. So as the left hand side equals the right hand side, the matrix equation is true for n equals 1. So assume now true for n equals k. And if it is true for n equals k, this will give me that this matrix is equal to this matrix. Okay. And what we're doing is, you know, we're showing it's true for 1. So when k is 1, this is true. And then when we show that k plus 1 is true, then we show that when k is 1 and k plus 1 was true, so when it's 2 it works because we show 1 works, so 1 plus 1 is 2, so it shows 2 works, and if 2 works, 3 works, and so on. So you know, it's quite a nice little proof, but people do kind of misunderstand it, but yeah, it is quite a nice proof. Right, so with n equals k plus 1, the matrix equation becomes, so now we're just focusing on, you know, the left hand side. So 3 minus 4, 1 minus 1, k plus 1, and that's 3 minus 4, 1 minus 1, k, 3 minus 4, 1 minus 1 to the power 1. And then I'm carrying up on the right, so I can replace that, substitute in for my matrix with k, so this is 2k plus 1, that's k, that's minus 4k, and minus 2k plus 1, multiplied by 3 minus 4, 1 minus 1. So we are multiplying here, so we've got, to work this one out, we've got this and this. So this times this is going to give me 6k plus 3 minus 4k. Okay, and then moving across to this point, we're going this way and this way. So minus 4 times 2k, so we got minus 8k minus 4. And then minus 4k times minus 1 is plus 4k. And then we've got 3k minus 2k plus 1, and we've got minus 4k plus 2k minus 1. Now let's simplify. So this gives me 2k plus 3. Underneath I get k plus 1. And over here I get minus 4k minus 4. And underneath I get minus 2k minus 1. Now we want obviously the n to be a k plus 1. So that's what I want to kind of bring out of it. So I want a k plus 1. So 2 brackets k plus 1. Then it'll be plus 1, won't it? Because this is 2k, 2, and we want 3, so it's plus 1 there. This one, if I bring the minus 4 outside, I get k plus 1 inside. This one's already k plus 1. And this final one is a little bit more difficult. So we'll take the minus 2 outside, k plus 1. And when I look at this, this gives me minus 2k minus 2. We want minus 1, so we must add 1. Now this is in this form, isn't it? So 2n plus 1, 2k plus 1 plus 1. Minus 4n, minus 4k plus 1. n, k plus 1. Minus 2n plus 1. Minus 2k plus 1 plus 1. Okay, so this now works. So therefore the matrix equation is true when n equals k plus 1, and then my conclusion. And there we have it. Just, you know, sometimes when I'm reading, spelling and writing at the same time, I kind of pause and make mistakes. So I did that off camera. Okay, so that's question 1 done. Now let's have a look at question 2. Okay, very much the same process. The only difference is the powers in that second matrix. Sorry, I just noticed there was missing an n up there in the question. 2, 0, 1, 1 to the power 1 is 2, 0, 1, 1. And then the right hand side, 2 to the power 1, 0, 2 to the power 1 minus 1, and 1. So this leaves me with 2, 0, 2 take away 1 is 1, and that one is 1. So there we have our first step. So now as the left hand side equals the right hand side, the matrix equation is true for n equals 1. And now we can assume that it's true for n equals k, which means 2, 0, 1, 1 to the power k is equal to 2 to the power k, 0, 2 to the k minus 1, and 1. So with n equals k plus 1, the matrix equation becomes, so it's 2, 0, 1, 1 k plus 1. So that's 2, 0, 1, 1 k times 2, 0, 1, 1 to the power 1. Now substituting in, so we have 2 to the k, 0, 2 to the k minus 1, 1, and that is multiplied by 2, 0, 1, 1. Now multiplying these, so we've got in this top left, we've got 2 times 2 to the k, and then we got 0 times 1. And then top right, we got 2k times 0 plus 0 times 1. Bottom left, we've got 2 times 2k minus 2. I'll do the 2 times 1 there in my head. And 1 times 1. And then we've got 2k minus 1 times 0 and 1 times 1. So 2 times 2k, this 2 is like 2 to the power 1 here, so this is 2 to the k plus 1. This is 0. This is 2 to the k plus 1. Minus 2 plus 1 is minus 1. And this is 0 plus 1, which is 1. Now this follows this pattern, isn't it? 2 to the n, 2 to the k plus 1, 2 to the n, minus 1, 2 to the k plus 1, minus 1, and then this is 0, 1, 0, 1. Okay, so therefore matrix equation true for n equals k plus 1, and then my conclusion. And there we have it, the final video in the FP1 series. Okay, yeah, let me know in the comments any questions, anything I missed out, or any mistakes you might have noticed. I will get round to fixing the mistakes that people have spotted. I have spotted a mistake right in the very first video of this FP1 series with a simple surd. So I will get to fixing that at some point. But I've been prioritising new videos over fixing some of the old ones. Anyway, don't forget, like, subscribe, and if you can, join. Otherwise, see you in another video.